Didn't you give me the tape?
Yes.
I think you did.
She said, well, sometimes when I've had something.
The pain this browser is.
Your ID is
Oh, choose the change.
What do I do with English?
change it. That's it. Yes. So the only way to go is to sign it. Okay. Right, well, let's make a start. We're certainly expecting more people than this, and I'm sure they'll appear in the course of time. But can I say, first of all, that that we will continue our usual habit of meeting in the Champagne Charlie wine bar after the meeting, which is on the Charing Station. If you have time to join us, you're all welcome. And now I introduce Alexei Lisitsa, is that right? Yes. University of Liverpool, who's been in this country for a decade, just over, yes. I'm thoroughly used to English climate. She says it's very wet, it doesn't have a proper winter. And he used to, yes, but there you go, they tend that back place. I know very little about Alexei's work, and I think there are most people in this country in the same position, so that's what we're here to. Your work and the work you've been participating in this evening. But I thought by it might be interesting to mention that I saw, quite by chance, I saw Alexei came in New Scientist 2 or 3 weeks ago, where it was reported that he has made a significant start on solving a very long-standing mathematical problem, which is called the discrepancy problem. Right. That's as much as I know. But we obviously have a very distinguished guest here. Thank you, Alex. And over to you. Thank
you, so good afternoon, everyone. So thank you very much for the invitation. I'm very honored and humbled to be here in this room. This remarkable group, specialist group in advanced programming. And the topic of my talk today is introduction to REFAL. So I would like to start with this disclaimer. While you can observe kind of rough outlines of doing the talk, I will just say that although I was invited after a search for experts in REFAL language, I have to admit I'm not an expert. In a sense, I didn't take a part in developing this language, and not at all, not at the smallest part. Neither have implemented nor just otherwise, I just suggested some design. But I've been using this language occasionally from time to time. And I found it, first of all, it's a remarkable language. It has a long history. Sadly, it's not got enough attention, so it has interesting features. And especially, it has also very interesting context in which it has appeared and is still undeveloped. So here is a rough outline of my talk. First part, I will say something about REFAL, language, and then the second part is my personal preferred topic in this area. To say something about supercompilation, and the reason being for such a combination that supercompilation as a technique has been developing over years in very close links with REFAL. Essentially, the same people who were implementing, designing versions of REFAL were doing also supercompilers for REFAL. Although there are some other languages, other supercompilers exist, but still REFAL is a kind of central focus of supercompilation development as a whole. Right, so that is the outline, and of course, no talk about REFAL would be right, correct, and complete without a few words about Valentin Tucci. Valentin has been a computer scientist and mathematician, and he not only been a philosopher, he also been a human rights and democracy activist in the Soviet time in the 60s and 70s. He was a founding member of Russian chapter of Amnesty International. He also raised the voice against Soviet intervention in Czechoslovakia and so on. And because of that, he was in particular good relations with the Soviet authorities at the time. So eventually, in 1977, he left the Soviet Union, Russia at the time, and since then, he lived in the United States. He became a professor in the City University of New York. Right, so, but we are here today mostly because of his invention. He was an inventor of REFAL. So he has proposed the idea to have such a language and was an author of the first implementation of this language. Right, so now I'd like just to refer to the Valentin's Tucci words, just his words, and that is somehow a very short explanation of his philosophical position in terms of generic principles of his philosophy. And his philosophy, I mean literally, he has published a book, two books, philosophical background, this philosophical background and philosophical research, so he made a contribution to philosophy, and that is one of the central topics of his contribution to philosophy. And by his own words, say, development of supercompilation, REFAL, and development in computer science was happening afterwards. So, like the instances of his general philosophical position. And his general philosophical position can be explained best of all in his own words. Citations I just split in a few items here. So, in particular, in very general setup, he says that consider a system of any kind. A system means here can be biological system, social system, some kind of computer system eventually. And suppose that there is a way to make some numbers of copies of this system, possibly with some variations. So you can think about some in biological context like mutations, for example. Now, and suppose also that you can take this system and join them together in a new system which is called S prime, which has an access to all these copies as their subsystems. Again, now I'm referring, say, to social setup. In social setup, you can think about developing, or say, a big state from a small nation groups. So it has a small nation group developing and joining together, and you get a large system. Now, it's a very general word, but I think it's important to just show where these roots of this particular language are coming from. Now, and then perhaps that was, well, in my opinion, the most powerful idea. Now, we assume also that this large system somehow has a mechanism to deal with all these subsystems. To deal with means it can mean different things. It can look in internals how it works. It can also modify again the way the subsystems works. So in this way you can, for example, model to some extent again social mechanisms. While large systems interact with its own subsystems. And now in that case, if that happens, then we call this S prime the meta system with respect to S. And the whole process of transition from S to S prime is called the meta system transition. So that is the basic, if you like, positions on teaching philosophy. An observation is made that when you have such a development, you may have several transitions of such a like to a hierarchical process. So as a result, you may have a multi-level hierarchy of control. So, right, so and upper systems have some limited, in some aspects more advanced control over subsystems, and overall together can demonstrate complicated behavior.
Yes. Would a change to a single S constitute a transition? Or does it have to affect multiple subsystems?
Well, it can be as simple as well, single as well.
Yeah.
So the main point in this meta system transition is that S prime has some access and control to S. It can observe its behavior, can make some decisions, can put some restrictions, can analyze its behavior.
Can I ask a question too? It says possibly with variations. So we can have removable identical copies of S in S. Is there any limit on the type of variations that may be acceptable within this time?
Well, it's a philosophical question, very difficult to answer. Well, of course, when you instantiate a particular situation, there should be some limits. But I personally would be reluctant to impose restrictions at that level. Who knows what else we can try to model in this way?
It seems that a biological metaphor would be fairly close to it. You're describing something that is
Yes.
like evolution.
Yes,
Although it isn't quite clear because the evolution changes occur in the individual subsystems rather than to not controlled by the animal system.
yes.
Whereas here, the implications that they are somehow controlled from a high level.
Yes.
That's correct. Is it?
Yes, that's correct. Yes. But at least to my understanding of this philosophy.
Right, you have other reading.
So now I just to jump in to say that indeed the quantum Tuchin has developed philosophy based on these positions as a consistent theory, and essentially has shown that major steps in biological and cultural evolution can be seen and explained and analyzed in these terms. So that was the topic of his main philosophical book, Phenomenon of Science, Cybernetic Approach to Evolution. And then just referring to some history, so the book, because at the time he actually written the book, he was already not in good relations with the Soviet authorities. Essentially, he had problems to actually publish this book back home. So eventually, after several years, 5 or 7, he was able to publish it in the West. So it didn't improve his position again in respect to relations with authorities. So this kind of remarkable story, of course, but in many aspects remarkable person. But today I would like just to move towards computing, and again, just take the word of Valentin to team. Meta-system transition in computing can be then instantiated to the following form. So essentially, when we have a transition from some machine, some computing machine, which can be, for example, well, a computer or a virtual machine executing some program, and we have transition to some meta machine that actually interacts with this machine. Interacts, in particular, means to control this original machine app, analyzes, imitates its work, and so on. So the idea is meta-system transition. You are talking about modeling or computation of a machine app at the level of some meta machine. But at the same time, has some control over this lower-level machine. So it's a very general position, and under this general position, many work on program transformation of meta computations what exactly fits into this definition. And that was a region of, in some way, if you like, philosophical background of development, which led to creation of REFAL. So REFAL ideologically was conceived as a language, universal language for describing this meta-system hierarchies, and two requirements were set up. Essentially, that was the goal. Again, in words of computing itself. On one side, we would like to make it simple enough so that one can deal with the REFAL machine, in fact, the REFAL in a way to would be a subject of theoretical analysis. So it would be not very complicated, not overloaded with many details, but simple enough just to be an object of theoretical analysis. And so that, on the other hand, we would like to make it rich enough for REFAL to be used as a real-life programming language to program real-life algorithms and so on. So there are two. Yes.
Two obvious questions. Firstly, I assume that REFAL, you could write a Turing simulator in REFAL. So
Definitely so.
And the other question is, 1968, you hadn't left the Soviet Union at that time.
No.
So what was the nature of the implementation?
Nature.
What did it run on?
Oh, right. So I don't know, some older machines.
A Soviet machine, or a Besson 6 or something like that?
Well, at some point, PL1 was involved, but I'm afraid not on 68. Too early. Some later versions were written PL1 or series. Yes. Yeah.
Yeah, this one was your
Yeah.
Yeah, but it was a clone of life about how I see it.
That's how what?
1996, something or other. And the R series was a clone of 360.
That's a lot.
Very much. Oh, you might be right. Oh, yeah, was
Yeah, I have to admit, yes, I have to look up what exactly it was running on at that time. I don't know when in 1987, I myself personally first time seeing REFAL, already the implementations for IBM XT machines, and it worked fine, and it was implemented for C. And it was working around language. Now, a short history, just to name a few versions of the language. In the 70s and still in the 80s, the most popular implementation was called REFAL. And now we can find, well, it's supported to some extent, because there are versions of around 2005, around, just rewritten all the implementations of REFAL 2. And so it gained popularity, and at this time, in fact, I read recently that it was a language of choice for AI community in Soviet Union. And what I witnessed by the end of the 80s, indeed, that was possibly the case, because I worked in a small institution, and we have an AI research lab, and there was almost everyone knew REFAL and actually used to do some day-to-day programming and implement some prototypes. It was really popular language in the 80s, not on a large-scale industrial programming, because all existed, but at least as in research labs, especially working with symbolic transformations and AI in general. Now, during the 80s, the language has been heavily revised and took very seriously by different teams of researchers, and eventually it led to three main dialects or three main implementations, which are still alive in the sense there are teams which support these languages and support these dialects, and well, they're slightly different in extensions of the language. But what is common in all these versions of REFAL, that they have kind of common background and common data model. That I would like to refer for the rest of this talk. I won't adjust to any particular REFAL here. I will be using so-called basic REFAL, which is well, still universal language. You still can program everything with this language, but it's free from later additions. So in some sense, it's pure REFAL. Although it's not called pure, the definition is called basic REFAL, a subset of all the dialects I mentioned here. Yes, and all these versions are available. So if you just Google any of these names, you will get directly to the website and download and run. So all of them are available both for the videos, the lines, for other applications as well. That is one really short overview of how it's been developing all the time. But now I would like to jump to the language definition. And I know because from my own experience in such a slide, you are tired immediately. And then, yes, but then I would like to demonstrate that the basic REFAL is pretty simple. So there is nothing, so that's essentially all grammar. And what else I would like to draw your attention on this page is that because it's functional programming language, it has the program in itself is just a definition of several functions. So it's reflected in the first line, and first definition actually also labeled this $entry, which means that will be entry from code. So when we try to execute this program, so its first call will be made as described immediately after entry. So that is somewhat that is the definition of REFAL. Now we will see some definitions and examples, and perhaps not worth spending a lot of time on this slide. But I would like just to show this perhaps that is a feature of the language which perhaps provide more difficulties is when we first look at that. So that's the way how the function calls are are actually written in the language. So it's angular brackets, and then we have a function name, and then the arguments for the function. So when you see typical REFAL program with a lot of angular brackets, this is just a function calls as the that is just distinctive feature of the language. And REFAL data, so I will explain on a few next slides. That is one of the strong points of the language. It's quite flexible way of the quite flexible data model. So essentially, there is some basic set of symbols, and what you can do with symbols, you can arrange the terms. Terms in standard meaning. Terms, you can take some terms or atomic terms and symbols and apply some constructors. And constructors here, there are only two of them. One is here, but actually we cannot see anything here because it's blank. Because you just omitted a menu. But in fact, formally, what's in between V1 and V2 is a term constructor, which essentially refers to as a concatenation. You can take any two pieces of data, join them together, and you get a new piece of data. You can also structure the data and put any piece of data in a bracket. And again, formally, it's a term constructor, but somehow it is missing term symbol. So it's just only brackets remain. Of course, you can formally write an F or V1, but it's not named in REFAL. So in this way, now you can imagine what you can build or what the typical data REFAL is dealing with. You have some symbols, you can concatenate them in strings. Some of the strings you can embrace by brackets. You can again concatenate some brackets, again embrace the brackets, and so on. It should be clear that overall you will get a kind of tree structure. Formally it's term, but tree, and that is essentially a data REFAL is dealing with. And it's convenient, and again, having in mind some meta computations, if you have a data under arbitrary structured trees, you can then easily feed the programming language itself into such a data. It has to provide enough.
Okay, so the tree structure is defined by the nested bracket.
Yes.
And that sounds analogous to what you do.
Very good point. So you will some slides.
All right. Okay. Are there any tags that are on in XML?
There are no tags as it is, but you can easily mimic. What you do, you actually do your brackets and then put the symbol. The brackets with the symbol just after the left opening bracket. Altogether, they play a role of the tag. So in this sense, yes, and that is a very good point, and that is, in my opinion, one of the possibilities which has to be explored and used in the future. So in fact, it's very convenient language for XML processing. After some easy translation from XML format to REFAL data, you get a very powerful language to manipulate such a.
And one other question on this slide. Where you have pattern, is that intended to apply matching function?
Yes. So essentially, it works as a pattern matching. Well, I will explain in a moment. So essentially, function definition is just a set of patterns. Left-hand side is a pattern, right-hand side is a functional body. Essentially, when the pattern is worked, as there is a matching, there is a call to the right-hand side of the expression. And yes, and that you normally expect in a functional programming language with this pattern matching.
That's analogous.
Yes, this mechanism works in the same way. But what is make it distinctive, and I don't know, maybe there are some languages, but so it takes as a built-in properties of concatenation. You all know concatenation is an associative operation, and so it's one of the reasons why there is no notation here. There is no need. You just concatenate as you wish. And that gives you some extra expressivity in patterns. It's allowing you by patterns to reach, say, some places in the trees. It would be difficult to reach if you faithfully model it by standard terms, not assuming associativity. But then you will need some kind of extra machinery in order to get some places. But I will illustrate this on an example of programs in a few minutes time. Yes, so I already said everything about data in words, but here it is a slide which essentially shows a typical data, well, how the data are constructed, some examples, and yet another analogy, just for different words, reading different fields, but there is a lot of work and research in unranking trees and operations. So essentially, these are unranked trees or hedges. When you just take several trees together, just a sequence of trees, or in other words of words. All these are very close to the large body of research about manipulation of such structures. But here it's a built-in data constructors and efficient ways for dealing with such constructors. So that is the data. Now, perhaps I will show this REFAL profile when I say, so that is what does the language itself, right? It's positioned among other languages, so what are some common features with other languages and some distinctive features. First of all, the functional programming language is a strict programming language in a sense, and so it's not lazy semantics. So whenever the function is actually called, whenever all parameters are evaluated. Yes, essentially over there. So you have to evaluate first parameters of the function, and then you can evaluate the function. Well, operational semantics indeed is based on a pattern matching. It means the function definition is a set of rules. Well, we can use the term rewriting rules for this specific terms. So you have left-hand side as a pattern, the right-hand side as a where this has to be rewritten. And these rules are ordered from top to the bottom. Essentially, whenever a function is called, the argument is tried against the top rule. If there is a match, it will be applied. If there is no match, it goes one step down. And so, if there is no match, then there's basically this function called is unsuccessful, then the whole execution stops. That is stop of the whole computation. So that's the idea, but we will see in examples, and perhaps it becomes more clear that I'm just referring to the small lesson tradition of the functional programming languages with the pattern matching mechanism. Another expressive mechanism which is quite useful in actually implementing some manipulations over this data is types of the variables. And there are three basic types. And types means here just referring to the values these variables can take. And by the way, also the illustration of naming condition here. So there are E variables, there's always E. Then dot, and that's the name, is a user-defined name, whatever you like. Something you want, E1, or E is some sensible name. So this type of things can take as its value any REFAL data, no restrictions whatsoever. The T name, we can take only values of the form which has a bracket, structural brackets on the top level. So essentially terms, maybe a variable of such a variable. While here, it's not only terms, but also lists of terms or forests or unrandom trees. And here it's atomic type is an S variable. You can take a variable in a symbol as its variable. And this separation is quite useful when you write some processing on such structured things. And again, we will see the examples how they come very naturally. And few remarks on pattern matching, although maybe it's a little bit ahead of what they actually used, but because we already use this question ahead here, we need some pattern matching. Essentially, we need to match some expression using these constructions and variables with other expressions. In order to be able to proceed with the execution. So here I'd like to illustrate that there is it's not entirely trivial in this way. And one of the non-trivial things is that solutions for such a pattern matching can be ambiguous. In the sense, there might be several solutions for such a pattern matching problem. One of the reasons because the assumption of associativity of concatenation. So what is written here? So it's written here we have E1, E2, two arbitrary expressions that take values from this variable. And we would like them together provide this AB. AB just atomic symbol. And we have three possible solutions here. Whereby these brackets I just denote for empty space. The empty space somehow also legal data value in the REFAL. So essentially, you have three solutions here. So then the question is, in order to proceed with the pattern matching execution, of course we have to find a solution. Then we have to take this value and pass them to the right-hand side of the rule. So which of them will be taken if we ever need to look at such pattern? Well, there is a quite definite disambiguation rules. So essentially, it works on the minimum length principle. So once we have such a question, the E1 will be tried for the shortest possible solution, and so on. So if in hypothetical case we have four variables on the left, everything will be tried from left to right for the shortest possible solution. Next you can write. That's the shortest. For E2 would be several variants. Again, the shortest solution for E2, each of them, and so on. So that is just some discipline, or in principle, can be taken in different ways. Well, I would say that for some applications, maybe I will return later on to this application, this policy may be too restrictive. For some of my applications, I would like here to be a bit more relaxed. To have opportunity to say iterate over different things, but then you need to apply specific mechanisms. You can enforce it, but then you need some extra programming on the code. But that is a basic assumption of the language. And finally, not finally,
Pure is intact.
you mean this one? Yeah, yes, the only semantic assumption here is the type of the variable. Because of course there could be on the pattern E1, S1, that would mean arbitrary expression, then just a symbol, then arbitrary expression. And again, some kind of Yes, in practical assumption, you just choose the smallest possible. Yes. So that is a derivation in this case. And now we are just arrived on the first program to demonstrate. And in fact, it's taken from the manual or REFAL 5. Perhaps it was Valentin Churchin himself. Exactly this syntax. I propose this syntax. So what's in here? So that is a very simple but typical program. So we have this entry position here. So we have a goal, function goal, which would, well, definition of function goal, then we have definition of function path, and that essentially we have two definitions of function. Because it's entry, so in fact, when this program will be started, this call will be made. There is no left-hand side here that essentially, well, the program doesn't take any argument. Everything is written on the right. What to do within this program. Now, the here out, in fact, is built-in function for printing out. So this is a side effect that will print out the result of what is computed. What is computed here in the position of its argument. So now when execution will start, the REFAL machine will go to the deepest and the leftmost call, the functional call. And it will go to the call, well, in fact, it's only one underneath of it, to the PAL revolver. So it will call function PAL, which is described here. And now it will try to match the argument, which is revolver, with all patterns on the left-hand side. So there are several expressions here. Well, you have the right rules for definitions of function. It definitely cannot match with the empty space, so it's not empty. It cannot match with the symbol, so it's not atomic symbol yet. It can match though with this expression. So there is a symbol, and there is the same symbol on the right, on the left and on the right. So this expression then will be matched. Simultaneously with this process, the value of E2 will be assigned, and this value will be, so if S1 will be R, S1 will be R, then revolver will be value of E2. So it will just take over leftmost and rightmost R, and the rest will pass to this code, which again calls to the same function. So it's recursion, standard recursion. So now you can imagine what will happen. So in which case it will return true. If ever. So
you return one symbol. When the innermost letter, the you put on either side, the innermost letter is just one.
yes.
And you get true.
So in this case,
This case will be false.
this case will be false. After 3 steps, it will be false. It wouldn't match any of these patterns to go to this one and return false. So essentially, this program just implements pattern processor or checking for pattern. Of course, here is the input is a hardwired. Of course, you can take it as the argument of the whole program and pass it to this function, and then you will get the result. Yes, so that was checked where the argument is the pattern. And it's a very nice way, and now I just doubt that you can do it in such a short program in any other language. I would like to challenge anyone to demonstrate program which will do the same.
Okay. J or K.
That what
The J or K are ridiculously concise languages. I mean, they're totally mad. They're just a set of symbols, essentially, which do this kind of stuff. But
yes,
it's sort of evolution of APL. It's complete gibberish. You can't understand it at all. So this is much nicer. You have a chance of understanding it.
yes. Well, for example, another language which I am familiar with is a Prolog. Prolog, if you model this as a list, standard list, you cannot do that nice. Because you cannot have easy access to the right-hand side of the list. You can easily read off the head of the list. But in order to get to the bottom, you actually need to do some traversal to the list. While here, just in one expression, you're just saying, well, I pick up one point on the left, one point on the right. Just make a simple checks and proceed further. So that is, well, might be a very nice example of what you can achieve with REFAL. It's another very nice example called reverse, even shorter, which essentially does a reversal of list of terms. And that use of types of variables. So essentially it says whenever you have any term, well, essentially just a function description, nothing else. But this function, when given some argument, it will split, will try, in order to match to this pattern, it will split of one term and then compute the rest, and then moves this term to the right and applies this function to the right. As you see, in this nice manner, you will just do this also again just one line. Perhaps some other languages also can do it, but again, this is quite nice. Well, of course, if you look in Haskell list, there is a built-in reverse, so you don't need to do such things. But if you don't use the built-in, then perhaps you cannot do that in that simple and nice manner. Yes. So here it's a little bit more complicated example. It's just the following. You have your structure, arbitrary tree, built in from brackets and symbols. What we would like to do to go through all these trees on all levels and replace all A's with all B's. Essentially find A and B back. So that is what it shows again that using this in practical facilities of the language, we can do it quite easily in four lines. If there is a separate A and then some expression, then we just replace it and call file and do it. That's easy, that's simple. If there is a not A and the rest, you just move it. So you just leave it in place, but apply file to the rest. And now here is the most interesting. If none of these options are not satisfied, then you need to have some structure. You need to have structural brackets and something inside. So in that case, you just make a call on what is inside of this bracket and put the result in brackets and make a call to the rest. And now it's easy to see, perhaps after a few moments, that indeed in this way, this recursive calls will actually traverse the whole tree and replace A with B everywhere. And it will return very fast and very easy. Now here, just some background apology, I'd like just to make an announcement without much details. That in fact such a way of execution in fact can be seen as some generalization of the nice theoretical model of computation, so-called macro algorithms, which are essentially string rewriting systems with some, well, with some rules how to actually execute them. So here, REFAL in its pure model can be seen as a generalization of these Markov algorithms on this nested structures. So that somehow answers the first point of criteria for this language. And it should be simple enough to be, you will be able to analyze what is going on. So it's close to the nice and well-established theoretical model. And of course, you can model anything, Turing machine, and any other model of computation here, but Markov algorithms are there just by definition. If you don't use the brackets, essentially, REFAL program is very close to the Markov algorithm. Now, that's a point that's already been made, that REFAL data are suspiciously similar to data in XML format. And the reason for that is very clear, and the reason again formulated by Patrick Chin and his unpublished paper around this topic. So essentially what we are doing in both cases, we try to organize substructures by brackets. And that kind of main principle behind XML and then REFAL data as well. In particular, it means that you can easily convert XML data to REFAL data. Roughly, very roughly, not taking into account, say, properties, such features of XML, but essentially you replace these tags, this opening bracket with some tag name, and again you take it into a bracket just to separate from the rest. Whatever may come here, say list of properties, you just separate it from the rest. And by the way, this slide also reminded me about one feature of the language, which I haven't mentioned. The feature is the language is all functions formally have just one argument. Then one place function, unary functions. And on the formal side. On the side, but you can easily model functions with many arguments. You just take your argument and brace it by brackets. So if you need, say, function with 2 or 3 arguments, you just take these arguments, everyone put in the brackets, take them together. So formally, it's just one tree or one forest. So it can be fed to REFAL function. On the other hand, all 3 arguments are in their places separately. You can deal with them separately by using appropriate pattern matching principles. So here's this idea as well. So you just put tag as something separate in the brackets. So then when you need to match it, you know that essentially here is the place for tag, so it can be unintendedly matched to something else, which otherwise we have. So by just making this observation, so Chin himself got a very good paper, and I have just liked this. It's very principled and essentially making this point. So to process XML data, you can apply REFAL as it is after just simple translation from XML format. Now that would be and here is just an example of one program, or rather definition of a couple of functions, the tag list, which essentially does implement the following query, or I would rather say a transformation for some XML input. So essentially, it goes through the whole XML document and create a list of tags such that for this tag, there is a property with a true value. So there is a concept of property, which is actually described after the tag. And so essentially, that would be the whole program which does the same. You actually implement this query. When you apply to translated XML document, translated to REFAL data, the result of this function would be exactly what we are looking for. Again, it's traverse through all these nested brackets, take exactly what is required, property is true, and continue with the rest of the structure. That's a nice example, and well, my opinion is one of the very promising directions to build this, to actually apply REFAL on a larger scale to real life problems, not just a prototype and interesting for execution of something.
So that does part of the job that we do in the XML parser.
Yes.
Like usually what an XML parser does is build a data structure representing trees and not leave it as a string. So that you then have a more efficient way of actually getting trees. Presumably there's no way of doing that.
But I would say quite opposite. Presumably because after single translation from your XML document, you can get a piece of result data in REFAL forest or REFAL tree. So in this sense, but REFAL itself is designed for efficiency to work on such data structures. So once you get this as a result of translation, you get all the facilities that REFAL can do.
Okay, so what you said was that you denote REFAL data as a string, but are you saying that internally it's actually built as a tree?
Yes.
Okay, so you get some efficiency.
Yes. And moreover, in order to keep this access from both ends, there is a double linked list there in typical implementation. So we have efficient traversal in all directions. Yeah, so I would say that it's very promising, has been noticed by this unpublished paper, but it's also easy to Google for language of processing XML documents. Now, I'm just like to ask what time is.
I think we've got something else.
Yeah, so that because there is quite a lot of material, so let's just put plan carefully. So that was a very short introduction in REFAL itself on a very basic level, basic REFAL programs. But what makes it the most interesting, from my personal viewpoint, is that so there are some tools and technologies available for REFAL which are very powerful. And that is one of the tools, technologies, or techniques, if you would like to name it, called supercompilation. I was told by an expert in the area, people who actually implement this, it's somewhat unfortunate name, because I assume something superficial happens or something super happens. And in fact, it's just a variation from supervised compilation. And that is a semantic-based program transformation technique which was designed by Turchin on our side of REFAL and our side of developments in this meta-system transitions philosophy, cybernetic type of philosophy, and somehow it was influenced by all these developments. So the goal here is a program transformation. So at the simple level, just give me a REFAL program, I run super compiler, I will get another REFAL program. So what's that? The point is you can get, you can use it for specialization, for example. In your REFAL program, you may have some arguments already given, or you know in advance that the first argument always is true. By doing super compilation, you may specialize this program. You have more efficient specialized program which doesn't actually, well, which is aware about this particular value in the environment. You can do it also for straightforward optimization. In many cases, when run through the super compiler, you get more optimized programs, simplified in many aspects. I will show just two examples. Now, while in general the principles here are very general applicable to different languages, but in practice it turned out that most of the development, not everything, but most of the development, especially in early years, was done in the context of REFAL, of this technique. That's why it's interesting here, that's why I would like to say something about that. And as REFAL concerned, this particular supercompiler, SCP4, is most advanced and been in the development for at least 20 years or so. It's been for generations of implementation of REFAL itself, with SCP2, 3, 4 versions. So that is the current version. So it works for a particular version of REFAL, particular variant, REFAL 5. And I was assured today by Andrei Dmitriev, after this version, that it won't work for other REFAL. It's a little bit unfortunate. But still, for other REFALs, there are some other supercompilers and people generally developing REFAL. So many of them are involved in developing variants of supercompilation. And also, there are around supercompilers for other languages, like I mentioned, Java and Haskell. But of course, at the level of sophistication of development, well, they cannot be compared with SCP4. It's been a very long time and tuned for basically, if you like, trained on many examples, then generalized and this new concept will be implemented. Very general for supercompilation. Now, what is going on in there in a supercompiler? Now, here I would like to refer to the introduction when I was talking about this meta system transitions. So here, supercompiler can be seen as a system upper level, which essentially tries, well, in general terms, if you take a function program, the REFAL program, and give it to a supercompiler, it tries to execute it. Even in arbitrary case, even when there is no input fully defined. It may be just program which takes some value x and do something. So supercompiler try to execute it, and of course, depending on the value of this argument, it may have essentially infinite tree of all possible computations. With x, say, longer than 3, length 3 or longer, you go one way. If it's shorter, you go another way. So in general, of course, this idea will lead to the infinite tree of possible levels. But then what happens in here, then it observes, supercompiler observes what's going on in the tree. One particular point is that when you hit a configuration, you have already been before. So that means essentially you are in a loop, and essentially this loop can be thrown away in a sense that if you are interested in computing something and terminating computations, then if you throw away such loops, you won't change a lot of behavior. So essentially, terminating behavior will remain the same. And unadventurably, you can expand a little bit the inputs on which the program will terminate, but well, it's considered as not very crucial here. But also, there are some other observations. For example, when you hit a configuration which is not exactly the same, but similar to some configuration you have been before. The exact meaning of similar can be refined in different ways. One of that can work in precise technical terms. For example, you hit some configuration into which you can embed. So there is some embeddability. So one, this tree can be embedded to another tree. You already seen before that. It's already an indicator of similarity in behavior. But the point is, by doing that analysis of this symbolic execution, supercompiler builds a finite graph of such configuration. So it's trying to do infinite unraveling, but from time to time unfolding this graph based on a concept of similarity between these parameterized configurations. And now once it's constructed a finite graph, from this finite graph, it can read some a new program, which essentially very semantically based transformation. The new program is not depending on the syntax of the original program, but everything happens here observing the behavior in a general context, not assuming anything about input. And that, in that way, the program is read, and in general, what happens here, by throwing away some cycle groups, you can expand a little bit input function. So it may terminate on some inputs in which the original one was diverged. But for terminating programs, it may result in quite deep transformations. And now I would like just to show some of the results you can achieve by such process. Again, on one simple example. And, well, I can even run it directly on SCP4, and I will just explain what's in there. So here, it's just a combination of two functions you already see. The one is a palindrome checking, and another is reverse. Now, if you take some argument, reverse the argument, concatenate them together, and apply the palindrome, so what would be the result? There's something, you convert it. Yeah, but even if it's arbitrary one,
Yeah.
if you reverse it, it's still palindrome. It's always palindrome.
Yeah.
So essentially it means it will return true everywhere. Of course, for inputs which match well, this pattern. Right. So what you would expect then after running exactly that program, you see that that's a program in a general position. So you do not give any argument. So arguments are not defined. So just a syntactical object given to supercompiler. After it's run, it does its analysis of all possible cases, it will return that outcome. So essentially, what it's saying is always return true. You may say it's just a simple tree. Well, I would say that it's not a simple. After all, that can be tailored for a particular program, but it's quite generic. So we have generic mechanism. And when you apply such a program, so I consider it quite vulnerable that you can get it just fully automatically simplification, realizing the combination of these two functions in fact doesn't do anything, it's always true. So that perhaps one of the simplest, remarkable applications of supercompiler. And that is prologue. So I would like to announce it, yes, supercalculation or optimization. So that was the time for that obvious optimization here. After you run it, you get a simple program which return immediately true, no need to go reverse and then check. It's much more, it's just optimal for this particular program. But slightly different angle, or slightly different angle, the same technology can be used for verification. And that, well, that I would say what made me attracted to this technology, we found in particular, and the supercomputation. And as always, as whole, Valentin Turchin already said everything here. So it is a great figure, so it kind of predicted almost all developments. So essentially here it's a simple citation saying, imagine that you have some program and you would like to establish that output always has some property. So essentially you would like to verify, say your program is working correctly, or you would like just to establish some property automatically. And so idea we propose is very simple, astonishingly in the power as this program. We have some function f of x, some implementation. We have some property p of x. And we would like to check, for example, f of x always has property p. What you do, so you may try to do. Of course, the first principles is clear, what works always. But if you have a powerful transformation technique, you can try to transform this one into identical two, as we just done in the previous example. So in this way, this is a general methodology how to establish properties of your program. Well, in this particular case, properties of the outputs of the program. And although it was proposed more than 20 years ago, until relatively recently, in just a collection of small examples, it shows that indeed, sometimes it works. You can prove commutativity of addition. If you encode addition of the unary notation, you can show by this process that it's always commutative. That's interesting, but what is turned out to me remarkable for this idea is that recently having tried for the problems more or less central for verification, verification of program properties and protocol properties and so on. And that I would like now to refer to our work with Andrei Unity, who is again one of the authors together with authors of the supercompiler. So what we have observed, in fact, we can use essentially the same approach to verify properties of essentially non-deterministic systems as well. Here, it's just, well, in the previous slide, it was just some function, no specification of what is there. In many cases, especially in protocol verification, you would like to verify that whatever protocol is doing, it will never get into that state. And the idea, what kind of modification of original idea of routine, what was proposed is just to model your system you would like to verify by the functional program, which essentially, for typical systems, say a protocol, even parameterized protocol, it's quite easy to write some executable specification for what exactly is used. So the idea is let us specify it as a functional program. And now we will write another program. We will check the property which we would like to establish for the protocol. And the simulating program, given, say, also number of steps we would like to simulate as an input parameter. Essentially, the program is saying, well, here is a protocol, give me a number of steps. Given a number of steps, the program will run and return the state of the protocol after n steps, which is, in most of the cases, it's easy, relatively easy to implement. So this is kind of testing scenario. You run it and then you check the protocol. But what is possible here, by using supercompilation, to do parameterized testing. So when you encode it as shown here, then you also can encode non-deterministic behavior. What does it mean? In some protocols, you're allowed to go, say, left or right, say, on n step. You can go one direction or another direction. So how you actually encode it into essentially deterministic programs? You just take another argument. The argument will say where to go, left or right, or how to make the choices as a branching point. So if I have only two choices, it will be just a sequence of left, right, right, left. Then given that argument, I can now model my system and then check the property. So that would be testing scenario. Parameterized testing, I would like now to implement everything in REFAL, and then I would like to return general statement that my program never return value. I always have a property by translating into the statement about our modeling functional program. So essentially, the statement is if the states always have some property, no matter how the protocol is running, you can then, by modeling a functional program, this function will never return the value false. Now, the statement about that protocol converted into a statement about functional programs. But now, this type of things, as you can imagine with previous example, one can try to apply supercompiler and to see whether this one can be returned into something which definitely won't return a value false. And what is interesting here, and why myself was very attracted to what we were not here, that in fact that it works. There are many standard classes of tasks interesting for verification community, using as a yardsticks of all technologies how you check the property. Many of that we can deal with this way. Now maybe just to saving a time, instead of going into details, just show the list. Well, if necessary, I can return to this point, being aware about time. I will just show some, well, this is just an encoding of a sum protocol, which was interesting, some cache coherence protocol, which you would like to show some safety property. You never get in a bad state. So essentially, well, that is an encoding in REFAL program, and well, essentially, after supercompilation, you get a REFAL program. It can be quite complicated, but the point is, there is no return false operators altogether. So essentially, it means supercompiler was powerful enough to realize whatever is going on, you will never get into this branch leading to the false probability violated. And it's done by unraveling all possible computations, taking into account, of course, work of this testing program, on the board. But then it's removed all false return operators. And now, assuming that everything works correctly here, you can then say that the original protocol is correct. So that is an idea behind these applications. And maybe I will just show what is doable in this way. Many of the standard examples of cache coherence protocols is a yardstick for any methods for parameterized verification. There are at least half a dozen different methods how you can verify them, so they relatively complicated at the same time as doable in an automated manner. So we can do in this manner all of them. The more complicated protocols of the same family, cache coherence, but organized in a different way, also can be done. And some other algorithms and verification Petri nets models and so on. And now, yes, so we have some understanding why it works, but perhaps I will skip it. I will just show again just some list of the results in this particular area, what is doable by using this technology. Supercompilation, well, for REFAL in our case, but later on, this experiment has been done also using Java supercompiler, which made them more accessible by wider audience, and so it shows that it's not specifically REFAL property that it's possible to do. It's if you like supercompilation as it is. And well, but I mention it here because REFAL is a language for which supercompilation perhaps is the most powerful as we compare with all other languages. Recently, we applied this for verification of cryptographic protocols and even to metamorphic virus detection when supercompilation serves as a normalization procedure. Because with metamorphic viruses, the main problem is that new generation of a virus may have a different syntax. So it's difficult to detect by standard signatures. So, but supercompilation can be used for normalization. If a program has a slightly varied syntax, but essentially is the same semantics, supercompiler will return absolutely the same outcome. Because it works not looking essentially at the syntax property, just trying to execute and analyze on the fly what's going on. So this way you can normalize the code, and presumably this is just a proof of the concept. Presumably you can do metamorphic virus detection. Yet another interesting application of all these technologies. Now I came to a conclusion. Well, I hope I have shown that REFAL is an interesting language. Can be useful in some contexts. It has a flexible data model, powerful pattern matching. Supercompilation is readily available, at least for some dialects of REFAL. Modern development tools and Eclipse plugins are also available, at least for REFAL Plus. Unfortunately, it's not available for REFAL 5, which myself was familiar with. But for REFAL Plus, you can use kind of Windows interface and run more or less standard development tools and so on. Well, and finally, implementations are also readily available. All of these mentioned versions, if you just Google any of this, you go directly to the site and download and run it straight away. Right, so that is the end of the talk. Thank you.
I think we do have to agree with your conclusion that it's an interesting thing. Questions? Well, I'll try one, which is that all compilers do global analysis of programs, but usually that analysis is not available to the programmer in any way whatsoever. And the supercompilation approach that you described here seems to make that global analysis something that you can actually is a tool of another program.
Yes.
And that presumably is, so you might call it meta compilation, an alternative to supercompilation.
Yes, I would say the supercompilation is just a particular instance of metacompilation. Metacomputation.
Yeah, okay.
Because it's dealing with the programs as an object. You give it a program, it's manipulate and return more or less equivalent.
And I can't answer this, but I can't think of a language that allows me to do that, but perhaps there are.
Well, at least as supercompilers, at least you can do it with Java to some extent.
Yeah.
You can do it with Haskell to some extent, in a similar manner.
Right.
Mainly because they are not for that long time in the development. They may not get refined in terms of what you can achieve. But essentially developing the same direction. And of course, if you are talking in general program transformations, there are a lot of other tools for partial evaluation, partial deduction, fraud, and concepts and tools also available. But based on slightly different ideas. So here, what I would like to point out is these ideas, how actually supercompiler works, is derived from a very general philosophical position. That's something quite exciting.
Sort of unknowing, I don't have any knowledge in this area. But it does sound like the normal compilation technique is a deductive process, where you can guarantee that what you compile into is logically equivalent when you unravel a loop or whatever you do to the original. It sounds like this one has got some kind of inductive element to it, where you can't guarantee that your thing is actually what you started with.
Exactly. Yes, and in fact, this is kind of very deep observation. And in fact, induction is deep inside of the whole process of supercompilation. And in fact, induction, kind of induction, responsible for what you can achieve in verification. Because essentially some inductive process goes, and how it goes, that's the induction. You develop your protocol, or you develop your configurations, and then you notice that you have been there. You do reference to a previous step, which is essentially, very roughly speaking, induction rules. Induction will refer to where have you been. But because it's very general and generic, and so
So the big question is, what is it actually doing?
Yeah, that's the hard question. How does it actually decide that this function that's being executed is the same as or similar to the one we've seen before?
Yes.
and it's not.
I mean, you've got what kind of sample input you're going to. I'm saying something about it. You take sample inputs, and you know, obviously, if you're not testing any edge conditions at that point, you're just.
It does sound like a whole problem.
Yeah, exactly.
I can imagine that one way of doing it is to look at huge corpus programs and classify them, and then pick out certain classifications. I don't know whether you're doing that or whether you're doing it in real time.
No, it's not trained against the kind of real corpus program,
No.
except in a very specific sense. What it happens over decades that when there is some programs which we would like to transform, you see as a human that it's doable, but current version of software compiler cannot do it. Then essentially, after analysis of few simple samples, you can generalize with some partial input and implement in the next version of software compiler. So it's not kind of automatic learning, but it's learning using human component. People who are doing this, and essentially they should be called to develop. Essentially, in this case, it was Andre Muted for SCP4, who was doing that over years. If something doesn't work, generalize or conceptualize what should be added, and it's added. So it grows slowly, but covering one. That's my understanding of how it goes and develops.
Which I'm sure we can say a lot more about. But any other questions anyone wants to ask? I think that in that case, we'll say a big thank you. Please make sure you sign the attendance list if you haven't already. Hopefully there will be a recording of this on YouTube after the event. And do join us in the wine bar if you have time. Thank you very much.
Thank you. Thank you.
Yes.
Very wide angle camera for that. Yeah. When you're over there, it's just about on camera still.
Sorry.
I don't know what it's done. Are you still pedaling on your prompter?
Yes. Yeah, should I
In fact, I was loving it.
Keep up my toe, and I worked out that it was sitting two spaces in the format. It was not quite right. You couldn't see it.